Hello everybody, this is the first of three videos covering the arenes and phenol topic of Year 2 chemistry. As you can see from the table on here, I've highlighted the particular aspects which are important in this topic, and today we're going to look in this first video at the structure of benzene, how it was developed, how models of the benzene molecule have come and developed over time, and the modern model that we consider to be as good and accurate a representation as we do have. We then go on and look at some aspects of naming arenes, and then in a separate video we'll deal with the reactions of arenes, the nitration, halogenation and so on, and comparative reactivity. And in a third video we'll look at phenol and its reactions as well. Okay, so to begin with, the story of the benzene structure. Okay. Well, benzene is one of several colourless, fragrant liquids isolated from coal tar, and hence the name aromatics, because they all have aromas, smells. And there were several interesting facts developed about this molecule by Michael Faraday. They found out that the molar mass of the molecule was 78, and it had the percentage composition 92.3% carbon, and it was a hydrocarbon. This meant, if you do the calculation, the molecular formula would be C6H6. And at the time, 1860, we didn't know of ring structures. So if you have a go at trying to draw a structure for C6H6 without any rings, then you come up with these three. These are three that I've come up with. And as you can see, we've got a chain of 6 carbon atoms and an awful lot of unsaturation. Triple bonds, double bonds all over the place. A structure C6H6 should be incredibly unsaturated. Think about it. 6 carbons and an alkane would be C6H14, but only 6 hydrogens. So we must have seriously unsaturation going on in our molecule. As a result of that, then of course, as with all unsaturated molecules, it should decolorize bromine solution when shaken with it, but it doesn't. Well, of course, that en passe in the structure required a certain bit of forethinking, and one Auguste Kekulé came up with this idea and proposed a ring structure of 6 carbons in a hexagon with alternating double and single bonds. The structure rapidly resonates or switches from one structure to the other. So half of the time a bond is double, half of the time it's single. So it's not really single and it's not really double. The Kekulé model, as you can see, 3 single bonds, 3 double bonds in a regular hexagonal structure. Well, that's fine until our technology developed and we were able to do some proper measurements on the actual benzene molecule. One thing we were able to decide was from X-ray crystallography studies that benzene is indeed planar, flat, with all the 6 hydrogens and 6 carbons in the same plane. So as you can see in this first representation, each carbon atom is joined to 2 other carbon atoms and a hydrogen. 3 single or sigma bonds have been formed. This leaves each carbon with a separate electron. These are still inhabiting carbon p orbitals, as you can see by the figure of 8 shape. So what we proposed, or what Kekulé proposed, was that the upper parts of 2 of these p orbitals would overlap and merge, and so would 2 bottom parts of the p orbitals. This gives the following structure. As you can see, we now have 3 pi bonds, the recognizable double bonds, which, as you can see in the middle picture, we've got 3 of them, along with the 3 single bonds. This was, of course, the Kekulé structure. Well, our modern model takes that one step further. rather than having three separate double bonds with three separate pi bonds, how about overlapping the upper parts of these pi orbitals into one ring structure above the plane of the atoms and another one below the plane of the atoms to create this idea: two rings of delocalized electrons above and below the plane of the atom. So the 12 atoms, if you like, 6 carbon, 6 hydrogen, joined by sigma bonds, are sandwiched between the two donuts, if you will, of delocalized electrons, which of course there are 6 because of the 6p electrons. Well, this model proposes identical lengths of carbon-carbon bonds. And when we were actually able to measure them, we found that indeed, yes, the carbon-carbon bonds in benzene are all the same. However, they're not the same length as single, and they're not the same length as double. They're in between. And so the evidence from bond lengths suggested that there couldn't be two different types of bonds because that would give us two different bond lengths. They're all the same and in between the length of single and double. Well, further evidence, of course, came from other experimental developments. Kekulé's structure, which we can represent as 3 doubles and 3 singles, and we now have a modern representation of the hexagon with the circle inside it, representing the modern delocalized structure. Remember, of course, there is a hydrogen attached to each carbon in a sigma bond, and in a skeletal picture such as this, we don't show them. And of course, it's quite a common exam question for you to give the evidence against the Kekulé structure, and we've already encountered 2 pieces of it: the lack of reactivity and the difference in the bond lengths. Well, of course, here's another piece of evidence. We take the idea of benzene, or the theoretical cyclohexyl-1,3,5 triene, the Kekulé structure, and in theory, if we hydrogenate this, that is, if we take every double bond in the molecule, here is cyclohexene, and we treat it with hydrogen gas and a nickel catalyst, we saturate it, adding a hydrogen onto each end of the double bond, making them single. The enthalpy change for this hydrogenation of a single double bond is minus 120 kilojoules. Therefore, if the Kekulé structure was correct, 3 double bonds would expect there to be a hydrogenation enthalpy of 3 times minus 120 minus 360. That's what we would have expected. However, when the actual hydrogenation is measured of real benzene, the value we get is only minus 208. We are 152 kilojoules lower than the expected value. Well, what does that mean? It means that the actual structure for benzene is 152 kilojoules more stable at a lower energy. So real benzene is actually much, much more stable than the 3 double, 3 single bond idea. And of course, this is accounting for the fact that our double bonds and single bonds have all been merged to create the delocalized structure, which we now recognize as being an accurate model. And so when we take a summary of the evidence against the Kekulé structure, as you can see, benzene is much more stable and does not undergo addition reactions, for example, with bromination, as an alkene would. This is because the benzene ring is very, very much more stable. The delocalized electron cloud protects the carbon atoms, prevents carbon bonds being broken, and only leads to substitution of the hydrogens on the ring rather than additions. We know that the bond lengths in actual benzene are all the same, but also in between the length of single and double bonds. double bonds will be shorter, single bonds would be longer. Benzene bonds are sort of halfway between the two. And the enthalpy of hydrogenation evidence was that the actual benzene structure is some 152 kilojoules more stable. The hydrogenation enthalpy is only minus 208, not minus 360 if it had three double bonds. So clearly it cannot have the three double bonds Kekulé structure. So our modern representation takes these facts into account and of course allows us to claim the new model, the new structure, doesn't suffer from these flaws as the Kekulé structure does. Now, naming arenes is a fairly complicated issue, so I'll only deal with it fairly simply. We can regard benzene, if you like, as the parent compound, and so we can see groups substituted onto that. The prefix in the molecule would be bromo or chloro or nitro, and the suffix would be the hydrocarbon benzene. So it's like you would say chloromethane or bromoethane. This is bromobenzene. For example, benzene is the suffix of the name. This, of course, is C6H5Br. We represent the positions on the benzene ring by numbers. We number the ring clockwise, starting at the top position where this bromine is bonded, and call that position number 1. And we move clockwise around the ring structure, counting as we go. So 2, 3, 4, 5, and 6 are the other positions. In this example, as you can see, we have two methyl groups substituted next to each other. And of course, we've chosen to represent these at the top position and the one to the right of that. These would be numbered 1 and 2. So this is 1, 2 with the location numbers, di telling me we've got two methyl groups, methyl benzene. So 1, 2, dimethylbenzene. Other examples where we have a prefix of a subgroup, this is a nitro group, the NO2 group, substituted on benzene as well. Now, the other versions of naming regard the use of the C6H5 group as a functional group, an aryl functional group, like CH3 would have been a methyl, or C2H5 would have been an ethyl hydrocarbon. C6H5 is referred to as a phenyl group, from the very old name for benzene, which was phene. So phenol is an OH group substituted on the benzene ring. And of course, it's a priority group, so it gets the ending ol. So to give this prefix to the benzene ring, phenol. Or in this example, where the substituted group is the amine group, then this would be phenylamine, as you can see. So we can use benzene as a suffix and phenyl as the C6H5 prefix.